Nice to meet you in our SGP online workshop. I'm Huaigu. I guess some of you already know me from our online workshop last year. In the last video, I talked about the basic theory of full waveform inversion, or FWI, using acoustic logging data. I also showed some simple FWI examples using the synthetic data. In this video, I will talk about the application of FWI in field data. Hope you can enjoy this video. I will use around 15 slides to introduce our work. At the beginning, let me briefly introduce the authors of this work. Now I'm a third-year PhD student in National University of Singapore. Elita and Arthur are my supervisors in NUS. Xinding is my supervisor in Southern University of Science and Technology. Actually, I spent most of my time in the last year in SUSTech. Before I came to SUSTech, I finished a 9-month intern job in Halliburton in Singapore. Ruijia and Xiang are my colleagues in the company who gave me a lot of support in this work, and I thank a lot to Halliburton for sharing us with the field acoustic logging data. The field data we have are monopole data collected by using the acoustic logging tool called Examiner Sonic Imager. We introduced the working patterns of the tool in our last year's video. You can check if you want to know more details. Let's review what full waveform inversion, or FWI, is. In our project, FWI is used for calculating the elastic model of formation rock around a borehole. The elastic model contains two elastic modulus, which are lambda and mu. By solving the velocity stress equations, which is a set of elastic wave equations, we can obtain the synthetic data of the elastic model. The goal of the FWI is to find the elastic model whose synthetic data can best match the observed data or the field data. The objective function in a norm 2 represents the misfit between the synthetic data and the field data. We use the gradient descent method to update lambda and mu to search a local minimum of the objective function. According to elastodynamic theory, lambda and mu can be transformed to p and s wave velocities with the help of density. Because we can obtain density of the formation rock from density log, therefore, searching the elastic model equals to searching the velocity model. Formation rock could be divided into two categories, which are fast formation and slow formation. If the S-wave velocity of the formation rock is larger than P-wave velocity of the fluid, the formation is called fast formation. Otherwise, the formation is called slow formation. The numerical simulation shows the elastic wave propagation in the case of fast formation. The red points indicate position of source transducer. Position of receivers are marked in pink. The waves traveling to the receivers are recorded as acoustic logging data. Let's watch the animation again. The fastest waves are P wave. These are S waves. P wave and S wave are body waves, and the waves traveling along the borehole with strong energy are surface waves, including pseudo-Rayleigh wave and Stoney waves. Now let's see how elastic wave propagates in a slow formation case. These fastest waves are still the P wave, but we notice that S wave does not refract it back to the borehole fluid. Therefore, the S wave almost cannot be observed in the data. There is also no pseudo-Rayleigh wave in slow formation cases. The strong energy belongs to Stoney waves. These are the synthetic data we just showed in the numerical simulations, which are obtained by solving the elastic wave equations. For the synthetic data of fast formation, we see the body waves are much weaker than the surface waves. For the synthetic data of the slow formation, the data seems simpler because of the absence of S-wave and pseudo-Rayleigh wave. Okay, we already have a basic understanding of these two categories of the data. Let's see how well this synthetic data can match with the field data. Let's see the case of fast formation first. The figure on the right-hand side is the typical field data collected in fast formation. We can observe both stable P wave and S wave. Then we can measure the P and S wave velocities from the field data, and further simulate the synthetic data according to the velocities. We do see some difference between the two data, so I picked up 3 pairs of traces at different offset to see the difference more clearly. These are the data at 5 feet offset. We see the synthetic data can well match the field data in the beginning, but the match in the behind is very poor. The figure on the right-hand side zoomed in the body wave part of the data. We see the P wave and the first arrived S wave are well matched in the two data. These are the data at 10 feet offset. Again, the first arrived P wave and the first arrived S wave can be well matched in the two data, but other part of the data cannot be matched. The features are the same for data at 15 feet. Because the travel time of the first arrived body waves are the same, so velocity model of the synthetic data is accurate. However, as I mentioned that FWI search the accurate velocity model by waveform matching. So currently, we cannot use the whole waveform, but only the first arrived body waves. Because automatically picking up the S wave in field data is always difficult, so up to now, we are only using the first arrived P wave in the FWI. The first arrived P wave in the two data are marked in red. When we apply the FWI, we cut off all the data except for the first arrived P wave. These are the first arrived P wave we picked up from the data. We plot them together and notice that the waveform can be well matched. Now let's look at an example of the FWI by using the first arrived P wave in fast formation. These logs are calculated by using field acoustic logging data from more than 200 measurements, which covered this depth range. We see the P wave velocity obtained by using near monopole data is slower than that obtained by using far monopole data. So we guess there is velocity variation in radial direction around borehole. We would like to recover the velocity model around the borehole. A starting model is needed to start the searching of FWI. This starting P wave velocity model is built according to the acoustic logs. The starting S wave velocity model is obtained by scaling from the P wave model by 0.5. This is the inverted velocity model after 50 iterations. We see the velocities near the wellbore become smaller than those in starting model. Let's look at the data collected in this region to see what happens. This is the starting P wave velocity model in the region. and this is the inverted Pwave velocity model. The field data collected in this region are plotted in black solid lines. The synthetic data of the starting model are plotted in red dot lines, and the synthetic data of the inverted model are plotted in green dashed lines. Let's first compare the black waveform and the red waveform. We see the red waveform tend to travel faster than the black waveform at near offset, and usually the near offset data are only sensitive to velocity model near the wellbore. So the low velocity area near the wellbore in the inverted Pwave velocity model delays the arrival time of the Pwave and makes the synthetic data better match with the field data. The decreasing objective function of all the measurements also indicates the Pwave data are matched better and better during the inversion. Now let's see the case of the slow formation. Again, we try to make the waveform of the Pwave in the synthetic data and those in the field data the same. But then we see the Stoney waves in the two data are very different. So we also only use the first arrived Pwave in the case of slow formation. This figure shows the Pwaves in the two data. We see that they are well matched. These are acoustic logs of a slow formation. We notice the highly possible velocity variation around the borehole, and we hope to recover the actual velocity structures by FWI. This is the starting model we built according to the acoustic logs, and this is the inverted results. Compared to the starting velocity model, the inverted velocity model has higher resolution, and we see more details about the structure of the low velocity area. We hope this velocity model, together with other logs, can provide more accurate geomechanical information. For example, the resistivity log in this region indicates the resistivity near the wellbore is also smaller than that far away from wellbore. And the natural gamma ray log shows the rocks in this region has low gamma API. Therefore, the area might be a sandy layer with fluid intrusion. Because of time limitation, that's all I can show in this video. The takeaway message of this video is that to match the synthetic data and the field data is the key of a successful FWI. If you are interested in this project, please look forward to our journal papers. Soon we will submit two papers. One talks about mathematics of this method. The other talks about the field data applications, which is more relevant to this video. And if you have any questions or you just want to discuss with me, you are also very welcomed to send me emails directly. I hope to see you again in the future. Bye bye.